So, today we want to look at this well known A star algorithm, and this was devised by Hart, Nilsson and Raphael essentially. So, out of these Nilsson is, I mean we have met these characters very briefly in the introduction. Nilsson is one of the founding fathers of AI along with Simon and Newell and Minsky and McCarthy. In fact, the first textbook on AI written around 1972 or so was written by Nilsson, essentially problem solving methods in AI, and it discusses most of the search algorithms that we have seen except the randomized algorithms and things like that. The best first search and heuristic functions and effective branching factor and all this kind of stuff was written in that book essentially. Nilsson was teaching at Stanford essentially. Hart, some of you may know because Duda and Hart, they wrote a very well known book on pattern recognition, and Raphael we had mentioned very briefly in passing. He was one of the first people to write a program to do automated theorem proving essentially. Anyway, so today we are interested of course in this algorithm A star, but for the moment we will just first call it A and then we will see under what conditions we can call it A star. Generally when we look at some of these algorithms, that star implies that it is admissible essentially, and by admissible we mean that it is guaranteed to find an optimal solution. So, branch and bound in that sense is admissible essentially. So, before I move on, our librarian informs me that my book, which I do not know how many of you have seen, is now available in the department library. There are about 5 copies and we are in chapter 5 of this book at this moment. So, you should catch up with that essentially. Okay. So, let us first get the motivation into place, which we have just discussed, is that you are at some start node S and you want to go to some goal node G, assuming this is a city map or something like that, and you have some kind of an open list. And there are nodes on this open list which you have to pick a node from for expansion. This is a old style algorithm that we wrote, depth first search, breadth first search, heuristic, best first search and so on. We did not use this terminology in branch and bound, but you can see that branch and bound also always picks the lowest node in lowest leaf in the tree that we were drawing, which is like an open list that you can maintain. Now, we saw that what best first search used was a function which kind of estimated the distance of every node to the goal node, and we call that function h of n. And best first search basically maintained a priority queue on the heuristic value and always pick the node which appeared to be closest to the goal essentially, and in the hope of finding the solution faster essentially. Branch and bound on the other hand keeps track of the partial costs found so far, which are these costs. So, these are actual costs, in a sense these are costs of actual partial solutions found. They may not necessarily be optimal, though for Dirac algorithm one can argue and prove that every time it picks a node it has found an optimal cost for that, but we will come back to that argument a little bit later. So, this is the actual cost that we have found to a given node so far essentially. So, if you try to visualize this as some sort of a physical system, you can see that branch and bound, like breadth first search, which was a simpler case of branch and bound, tries to stick as close to the source as possible, always picks a node which is which has the lowest known cost essentially. So, it tries to stick as close to the source as possible. So, it is like a pull on this thing which is pulling it back essentially. Best first search on the other hand always tries to go as close to the goal as possible essentially, because it is using the heuristic function which is an estimate of a given node to the goal essentially. So, in some sense that is a pull in that direction essentially. What we want to do in this algorithm A star is to use a combination of these two pulls, and that is as simple as that. We just need to fill in the details essentially. So, in A star terminology, this value is called G of n, and it is the actual cost of actual known cost of a path which is from S to n. So, this actual cost for this path of S to n, the kind of paths that we were drawing in Bunsen bound, we will call G of n. The cost that we were using in Bunsen bound, we will that label we will call G of n. H of n is an estimated cost of the segment from n to g, that we have used in best first search. The H of n tells you how far this goal is from the goal node essentially. So, in this algorithm A, we use a function called f of n, which is basically the sum of g of n plus h of n, and essentially we keep the priority queue sorted on this value of f of n essentially. Now, notice that what is happening in this search algorithm, we are starting with the source node or the start state, and we are gradually making this implicit graph explicit essentially by a kind of a search tree that we are generating, and whatever we have made explicit is divided into two parts. One is called the closed set or closed list, which is the internal nodes, and the other is the leaves, which we call as the open list. As we build this explicit graph, these g values are computed, because as we find partial paths we can compute their values, and that is the g value. The h value is independent of what we are doing. H value is simply a property of a given node. So, it is like saying how far is Mylapore from Chennai Central. We are just asking that question. There is no question of paths here. Some measure, we said Euclidean distance we can use or Manhattan distance we can use. A heuristic function is just a property of the node. So, the algorithm that we will implement, this A star, every time we generate a node, you can simply compute its h value, which is this heuristic value once for all, and you are done with essentially. Whereas, this g value may change. Why? Because you, as we saw in the example, first you may find a cost of length 15 to a node, and then you may find another path of cost 14 to that node. So, g of that node may change from 15 to 14. So, it is a quantity which keeps changing. So, it is the actual known cost or actual known cost of a known path, I should say, because there is some path that you have not yet explored and which could be cheaper. Now, we use these terms f star of n is equal to g star of n plus h star of n, and these are optimal costs. So, whenever we use the term star, they just denote the optimal cost. We may or may not know them essentially. In fact, we do not know them most of the time essentially. Even if we have found a path from some node to some intermediate node, we do not know what the actual cost. What is the relation between g of n and g star of n? Is it equal, lesser than, or greater than? Greater than? How many people feel it is greater than? Only one. You said greater than, right? Greater than equal to. Okay. Why greater than or equal to? Yeah. So, g of n is the path that you have found to that node n so far. It may be not the best path. So, it could be cost greater than g star of n essentially. So, this f of n is basically, or f star of n is the optimal, the cost of optimal path that starts with the start node, goes to node n, and then goes to the node g. So, for any node n, f star of n is the optimal cost, optimal path cost which passes through the node n essentially. And if that path is an optimal path, so if okay, so there is a distinction between these two. Here we are saying that for any node n, what is the optimal cost going through that node n. Here we are talking about an optimal path from S to G. We can assume that if this is equal to S n 1 n 2 n k g, then we can write f star of S is equal to f star of n 1 and so on f star of g, because it is the same path. Remember, when we say that this is an optimal path, then whether we say f star of any node on that path or f star of start or f star of goal, they will have the same cost, because this is only one path that we are talking about. So, for an optimal path, this holds, which we will use at some later point. G star is admissible if now we come to the same question again, the relation between h of n and h star of n. What should be the relation? So, I am giving you two options here, so we do not have equality. So, we have included inequality in both the sides. Which one is better, the first option or the second option? What should my heuristic function do? Should it, what is this one doing? This underestimates, and this overestimates. And I am making a claim, and this claim we will show more formally probably in the next class, that if I choose the right condition here, then the algorithm A star becomes admissible, and by admissible we mean it will find you the optimal cost path essentially. So, should my h of n be an underestimating function, which means h of n should be less than h star of n. Remember, h star of n is the optimal cost of going from n to the goal, or should it overestimate the cost of going from n to the goal? Which one will make my algorithm admissible? Should I take a vote on this, or is somebody going to volunteer an answer? So, let us take a vote. How many people feel it should overestimate the cost? Only one. 2 I think. So, can I use negation by failure? No. How many people feel it underestimates the cost? A very small number essentially. So, we will come back to this. So, let me take an example to illustrate this whole point essentially, and then you will see, or let me put it this way, it is an analogy that I often tend to use, that supposing you are buying a new, you want to buy a new mobile phone, the most popular object nowadays, and you want to get a, you have decided what phone you want to buy, but there are 3 or 4 shops which are selling it. So, you go to the first shop and let us say, I do not know what is a good price for you people. So, let us say it is 10,000 rupees. This fellow says I am giving you this phone for 10,000 rupees. Now, there you have some estimate of how much the other people will charge. Will you go to them if you think they charge less, or will you go to them if you think they charge more than 10,000? Charge less essentially. Okay. Which means that you think that they are under that the value of that node is underestimating the cost essentially. So, let us try and look at this example. Let us say there are only 2 nodes in open. Let us call them A and let us call them B, and let us say this is the actual path found to them, and let us say that they are just one step away from the goal. This is just to illustrate the idea. So, that is the edge that they are just likely to explore. Let us say that this cost is 100, just to simplify matters, let us say this cost is also 100, and let us say that this cost is 40 and this cost is 50. That is the edge cost. AG is the cost of edge AG is 40 and the cost of edge BG is 50. So, what do we have? We have this 100 is equal to G of B, this is also equal to G of A, and that is the actual cost. We do not, that is how that is, you might say, the H star of A is 40 and H star of B is 50. In this case, of course, if there is only one edge, it basically boils down to the edge cost essentially, but it could be more than one edge in principle. So, let us look at examples of both these functions. So, let us say H1 underestimates the cost and H2 overestimates the cost, and let us pick functions which are not very good, in the sense that both of them are giving you wrong information. Both of them are telling you is that B is actually closer to the goal than A is closer to the goal. So, let us work with this. So, H2, so let us say H2 of B equal to it is actually 50. So, let us say this is 70 and H2 of A is actually 40, but let us say it is 80. So, what does this mean? That this function H2, which is a heuristic function. So, remember we did this example with this blocks world, where we tried 2 different functions and we saw that one of them was better than the other. This is looking at another aspect of heuristic functions, which is one of them is underestimating and the other one is overestimating. So, first we are looking at a function which overestimates the cost, which means that this actual cost for this is 50, but this function thinks it is 70. The actual cost for this is 40, but this function thinks it is 80. So, in actual practice A is closer to the goal, which means this path should have been better, but this function will think that B is closer to the goal because of the estimate it has. H2 of B is 70, which is less than 80. So, F2 of B will be this g of a which is g of b which is the same is equal to 100 plus 70 equal to 170 and f 2 of a is equal to 100 plus 80 equal to 180. So, remember that we said that basically what this algorithm A star does is it maintains the priority queue of on f values essentially. So, in this small example there are only two nodes in the open list, one is A, one is B, and it has to decide which one to pick. It uses this f values, f 2 is 180, f 2 of A is 180 and f 2 of B is 170. So, it will pick this node, which means it will now what Dijkstra would have said relax the edge here, which means it will compute g of g. So, g 2 of g is equal to g 2 of b plus the actual cost, which is sorry which one have you picked? We have picked b, which is 50, correct. The actual cost was let me which is 50, which is the actual edge cost, which is equal to 100 plus 50 is 150, and h 2 of g is equal to 0. We assume that our heuristic function can at least tell us if you have reached the goal. So, the heuristic value at the goal is 0, which means f 2 of g is equal to 0 plus 150 is 150. So, what has happened in our search space? We started with S, then we had these two paths, this A, this is B. Then our algorithm H 2 has picked B and found a path to G. Then we have these two nodes on open A and G. A has a estimated cost. Now, estimated cost we mean the complete cost of going to the goal via this node A is estimated to be 180, because the heuristic estimate from A is 80 and the cost up to A is 100. So, 100 plus 80 is estimated to be 180. The estimated cost of G is the cost found so far, which is the G value, which is 150. So, here we have this node sitting with 150 and this node sitting with 180. So, the algorithm will pick G and terminate. The same algorithm that we talked about in the last class, when the completely defined solution becomes the cheapest, it will automatically get picked in this priority queue and then the algorithm will terminate. So, it will find this path essentially. Let us try the other option, which is H 1 of A. It underestimates. So, let us say H 1 of B equal to, it is actually 50, but now we are underestimating. So, let us say it is 30 and H 1 of A is actually 40. So, let me say this is 20, it is actually 40, but let us say this function thinks it is 30. So, in a manner H 2 and H 1 are similar, that both of them think that B is closer to the goal. The only difference is H 2 overestimates the cost and H 1 underestimates the cost essentially. So, in which case, as you can see, f 1 of B equal to 20 plus 100, 120, and f 1 of A is equal to 130. Again, this is a very similar situation. This algorithm, so originally this was 180, this was 170 and this became 150. With this new algorithm f 1, this is 130 and this is 120. So, again this algorithm will explore B first, but what will happen now? After picking B, it will relax this edge from B to G, which actual cost is 50. So, G to G or G 1 G is equal to 150, which means F 1 G is equal to 150. See, after they have found a path going from S to B to G, both of them know the actual cost. There is no longer this estimation done by H, because H is 0. So, the actual cost. So, F 1 G is 150 as well as F 2 G was 150. But now you can see that this is with the same cost 150, and this algorithm, let us call it A 1 star, has to choose between G and A. It turns out that A is lower estimated cost 130. So, this algorithm will pick A, and when it picks A, it will find a cheaper cost to G, exactly like Dijkstra's algorithm would have done, and this cheaper cost is the cost of 100 plus 40, which is 140. So, this will revise this cost to 140. Originally the estimated cost was 170 and it got revised to 150 here. Here it was 180, it never got revised to 150. Here it was 120, it got revised to 150, but when this expanded this, it got again revised to 140 essentially. And at that time, this is the only goal, only node left in our open list, because we have finished with A, we have finished with B both, and only G is left, and G will be picked with the cost of 140, which is the optimal solution. So, you can see that using H1 of H1 we could find the optimal solution, using H2 we could not find the optimal solution, even though both of them thought that B was a better choice. Using H2 we picked B and then we picked the goal, using H1 we picked B, but then we were forced to pick A and then we were forced to pick the goals. So, we found the optimal cost. So, this is the criteria we are looking for. This thing. If H of n is less than or equal to H star of n. So, the algorithm is admissible if the heuristic function underestimates the cost to the goal. So, let us just quickly describe the algorithm completely, because there are one or two things which were not there in the best first search algorithm. So, I will do a quick description and then we will do it, we will take it up again in the next class essentially. So, the algorithm is very similar, except that we keep track of these costs explicitly, G of a node and H of a node and so on. So, the steps are very similar. So, I will just write the outline here and you can fill in the details. So, I will just very briefly write open gets S, which means open gets the start node, but we want to keep track of parents and so on and so forth. So, let us just write here parent of S is nil, and H of S is computed. We can always compute the heuristic value of a node. So, as a matter of principle we compute the heuristic value and we initialize close to nil as before, except that here we have talked of this parent pointer rather than having this node pair that we had earlier. You can use that, it does not really matter. This is simply easier to describe. So, as before, if open is not equal to nil, pick best node n and add it to closed. I will just write it as an outline. I want to focus on the part of what do you do with this node n essentially. So, if n so if I use the older terminology, if goal test n, then reconstruct n. So, we assume that we can trace back the path and reconstruct the path, and then so all that is very similar to what we did in the earlier search algorithms. Else successors is a move gen of n. So, I am using the same functions that we had defined earlier, and for each m in successors we do the following essentially. So, let me also draw the situation at the point where this algorithm is doing working. So, this is S, and then somewhere we have this open list, which is a set of open nodes, and let us say this node n is here. So, this line that I have drawn represents open list, and we pick some node with the lowest f value. Have I said that here? Okay, I have said best node n, and by best I mean the lowest f value, and f is g plus h n, and it was not the goal node. So, we generate successors. So, let us say these are the successors of n, all neighbors if you want to say, or what are reachable from there. Now, you can see that there are three kinds of nodes here. One is one kind which is on the open list already. So, these two I mean to draw is that they are already on open. There are some which are already in closed, and there are some which are new nodes essentially. So, this one represents that new node essentially. So, for each m, so case 1, m does not belong to open and m does not belong to closed, which means it is this node here that I am talking about. It is a new node that has not been seen earlier essentially. Basically, we want to add it to our search space. So, what do? We say add compute h of m, then so we have some heuristic function that we use. Then we say parent m is n, and g of m is equal to g of n plus, I will use k as a cost function, so that k of n m is the cost of that edge going from n to m. So, we update the value of, or we compute the value of g m equal to g of n, the g value of the parent, exactly as we were doing in this branch and bound kind of a thing, and then we compute f of n and we say add n to open. So, there are three cases. The first case is when m is a new node. So, we compute its h value, we compute its g value, which means we can compute its f value. We mark the pointer of m as its parent that it came from and add it to open essentially. The next case that we want to look at is when it is already on open. So, case 2 M belongs to open, which means what, that we have found this edge here. So, we have dealt with these two cases. So, now if this were one of these two was M, it means it is on already an open, which means it already has a G value and H value and a parent pointer. So, this N has just been expanded. So, before that this was pointing to, let us say this one for argument's sake, let us say this was pointing to this and this was pointing to this. So, they already had this parent pointer. What do we do for such nodes, or what do we want to do? We want to see if we have found a cheaper path to that node or not, correct. We already have a path to this node M, it is coming through some sequence of nodes and all we remember is the parent pointer here. So, it already has a G value and an H value as well. So, if M belongs to open, then we do a check if G of n plus this value k of n M. What is this value? This value is a new cost that we have found to this node M. This node M was already on open. If this is less than the cost that was already stored for M, remember it is on open, so it must be having a G value. But if this new cost that we have found is better than the old cost, then we have to do some readjusting of pointers, which is that parent of M becomes N and G of M becomes this value, and F of course becomes in all this H of M is not changing at all, because it is just a property of that node N, it is not a property of that what path we have found to that node. Yeah, so these are the two cases. One case is for new nodes we simply add them to the graph, so to speak, create the parent pointer, compute the G value, compute the H value, compute the F value, and we are done. If we have found a new path to a node in open, then we need to check whether this path is better, which is what we are doing here. If it is better, then we readjust the parent pointer and readjust the G value essentially. So, this is where we are readjusting the G value, this is where we are readjusting the parent pointer, and then this of course taking into account the new G value. Case 3, M belongs to closed, which means you had already visited M and expanded M and generated children of M and so on and so forth. So, let us take this as a case. So, let us say now this is M, which means it was already generated before, which means it could have other children. So, let me use a different color here. So, this node could have been a child of M and maybe this node could have been a child of M, which could have its own child here, anything is possible essentially, right. The difference between a node on open and a node on close is that a node on close may have children of its own essentially. So, these purple nodes represent children of M essentially. So, if M is on close, first of course, we have to do what we did for case 2. So, first I will say do like in case 2, which means that this node M we have found a better path to this node M. Originally this M had some other pointer, let us say this pointer. So, remember these are pointer to parent nodes. So, M was pointing to its parent here, and if we find a better path to M, we must shift this pointer here and say that this is a new parent, exactly like what we did for n. Originally this node was pointing to this, but now we have removed this and we have said this is a new pointer, if we have found a better path through that. Likewise for closed nodes actually. So, do like in case 2. So, if so let me use this, if better path found which basically means this condition g of n plus k of n m is better is less than g of the old value of m, then so actually I should do like this, then like case 2, which means readjust the pointer parent pointer, readjust the g value, but now the g value has changed essentially. So, we need to, so just to take an example, if the old g of m, let me say old is equal to 50, and if g of m gets a new value which is, let us say g of n plus 10, and let us say g of n is 20 equal to 20 plus 10 equal to 30. So, if the old value was 50 and the new value was 30, then we have found a new path to this m which is 20 units cheaper than the old path, which means that all paths going from m to other nodes, we must pass on this improvement to them essentially. So, we must reduce the cost of this by 20, reduce the cost of this by 20, and then reduce the cost of this by 20, and so on and so forth. So, I will just write this and propagate improved cost to subtree below m. How can you do this propagation? You can just do a depth first traversal or something like that of this purple tree which is rooted at this m, which means this part of the tree. So, this node to this node to this node, that improved cost must be propagated to them. So, that is the third case. If you have found a new path to a node in the closed, a better path to a node in the closed, then that improvement has to be passed on to children of that node essentially, which was not the case in Dijkstra. I mentioned when we were talking about Dijkstra's algorithm that if you have found a path to a node in Dijkstra's algorithm, you have already found the optimal path to that, but in A star that is not the case essentially. Like we saw in the example that we saw, if you have found a path to G which was through the node B, which was a more expensive path, you can find a new path to that node essentially, and it is also possible for nodes in closed. You can easily construct an example. So, we need this extra step, that if we have found better paths to nodes that we had already expanded earlier, we need to propagate this improvement to their children essentially. So, which is a little bit more work than case 2.
So that's M. In case 1.
Where? This one. Yeah. And here, no, that is all. And add m to m, correct. So, under the conditions when the heuristic function underestimates the cost to the goal, this algorithm is called A star and it is admissible essentially. In the next class when we meet, we will prove that it is admissible. So, this is one of the few cases where we will give a formal proof of admissibility, because A star is a very well known and often used algorithm. But this is not the only condition for admissibility. I mean, this was the condition only with respect to the heuristic function. So, what we have shown with an example today, that if a heuristic function underestimates the cost of the goal, then the algorithm is admissible. And you can see branch and bound is a special case of A star, where h of n is always 0. That is why we said that you can think of this as an estimated cost. If you just assume h of n is 0 for every node, then this algorithm becomes branch and bound actually. But this is not the only condition. So, what I wanted to do is to think, just imagine that. So, A star is actually, some people just call it graph search. It is a weighted graph and you have to find the least cost path from one node to another node. We make some simplifying assumptions, but it is different from Dijestra's algorithm in one respect, that Dijestra's algorithm assumes that the complete graph is available to you, and it is a kind of an overkill in the sense that it finds the shortest path to every other node from a single source essentially. We are not interested in to every other node, we are only interested in finding a path to a given goal node, and we do not have the graph available to us. The graph is generated on the fly as we go along essentially. So, somewhere we have this function, move gen function. The graph is generated as we go along using the move gen function. So, we start with some node, we keep adding more nodes to the graph and then we work with it. Under these conditions, A star is a little bit different from Dijestra's algorithm. It also uses this idea of a heuristic function. Dijestra's algorithm did not need to do this, because it was anyway going to find shortest paths to all nodes in the graph essentially. It did not have a goal in mind. A star has a goal in mind, if you want to say it has a goal in mind, and therefore, it benefits from the use of a heuristic function. And if the heuristic function is an underestimating function, then that is one of the conditions for admissibility. So, I wanted to think of what other conditions you might require for admissibility. Just imagine that this is some arbitrary graph search problem, some graph is given to you, and under what conditions will this algorithm find an optimal path, and we will take this up in the next class. We will do a formal proof of this essentially. After we do that, we will compare heuristic functions again formally and show that heuristic functions which are more informed, they do lesser search. So, remember that when we were talking about branch and bound, we said that this estimate must be as high as possible. It must be a lower bound, even this is a lower bound, but it must be as high as possible. And we will formally show that the higher the estimate, the lesser the number of nodes that this algorithm will search before termination essentially. So, we will do these two formal things in the next class. Okay, so, we will stop here.